and pip install DNS Python, right?
Yep.
Presumably you got Tellurium. And then all you do is import Mongo methods as MM. And then there's a query, number of nodes in the network and whether it's an oscillator or not. So that gives you the IDs, apparently. Then you create a query which has the ID number, and then you can pull down the antimony string.
But how do I know the ID number?
They come from here. Yeah, let's try it, shall we? Let's see what happens.
So just a for loop.
Yeah, I guess so. Yeah, let's try it, shall we? See what happens. Well, I don't have the. Oh, there's a comma in there.
This is close. Next to true. Remove the parenthesis.
Yeah, there's a typo then. Oops, where did it go? Yeah, come back. I don't have Mongo methods anyway. So I don't have those. So you have to install her. Where is it? You have to install her Mongo methods, which is you have to install that.
Oh yeah.
By installing, really, just copy actually. So if I copy this.
Yeah, you put in the same folder.
And then new. Save as. I wanted to go there. It's called Mongo. Well, I better get the name.
Mongo method. That'd be there.
Oops. Mongo methods. Okay, so now if I run it, what? Why doesn't it? Why doesn't it find it? Do I have to do something else?
Is this in the same folder?
Oh, that might be. Yeah, that could be it. Yeah, it's not.
Yeah.
Test Mongo. Okay. So it's okay. So it's got the database. So the model IDs. There they are. These are all the IDs.
How many? Oh, so you only have like 20 models?
This is for 3-node models.
Oh.
Ask her for more if she has more. Which ones do you want to look at? The 3-node ones?
Oh, there's a number of nodes there.
Yeah. I don't know what she's got. So.
Wait, so 3 nodes mean 3 species?
Yes. There are no 3 ones. I guess there's no 5 ones either. No. Okay. You perhaps want some more, do you? What do you want? Yeah, I mean that's not enough, is it?
No, it's not. Probably like 100.
63.
Yeah.
Yeah, I'll ask her for more then.
Yeah. Maybe 2 nodes. What about 2 nodes? I don't know.
She can run it on the higher cluster. Just ask her if you need more. Okay.
Yeah.
And she can generate more for you. Anyway, once you got the ID, you can get the antimony model, or the SBML model, up to you. So.
Wait, so I can probably get the one that's the oscillator and the one is not as well.
Well, the one that's not will just be random. Yeah, and there it is. There's the model. So if I do print and you'll see that. There you go. So you can either create a picture of this, or you could just pull this piece out.
Well, actually, yeah.
And use that as a training. Use that as a train. Oh no, just get the stoichiometry matrix, right?
Yeah. That's
okay. So R equals T load a ant. Okay. Then get full stoichiometry matrix. There you go.
Okay. Yeah, that's much better.
Okay. So use that as an image.
Okay.
Yeah. Okay.
But well, like if uses the stoichiometry matrix, you can put in Coyote or no?
Coyote. No. No, Coyote accepts SPML.
So how you read this into Coyote?
You have there's another method here to get the SPML instead. Here. Then once you have the SPML, there's a special plugin that can load in. If you have a whole load of these XML files in a directory, it'll load them all in at once and then generate pictures for each one.
I see.
Okay. Talk to Claire about that.
Okay.
All right. Okay. So, what are you going to do today? Yes, where did it go? I had a thing here, it disappeared.
Oh, did you just delete it from?
I don't know. No, well, I'll bring it back. Where is it? What's this one look like? No, let's get this one. Okay, so what I want you to do is, first of all, given this, so I'll put this model in the chat, okay?
Yeah.
Chatty. Let's chat over here. So that model's in chat, okay? So first thing to do is to look at this model. I'll wait for you to get it from chat. And maybe you could draw it out on a piece of paper and then show the paper up on the camera, okay? Like, you know, show it up. Draw the pathway out, okay?
Okay.
Obviously starts with x0.
So, oh, I mean,
Anybody got a drawing?
it's just x0 to x.
Oh.
Well, x0 has a dollar in front of it, so it means it's fixed.
Yeah, constant.
What have you got? Oh yeah, show me. Close up.
It's too dark or something.
Close up. A bit further back because it's out of focus. More. Further back. It's out of focus. Yeah, it's completely out of focus. Doesn't want to focus. Oh, there it is. No, it's a bit too small though. Okay, so you probably got something like that.
Yep.
Right. Okay, so there's something missing from this though. If you look at the first rate law, what do you see?
Which one is third rate? The K2?
First rate law is this.
Oh, the first. Okay.
The second one is just simple linear mass action, right? Nothing special about it. But this one is a bit different. What do you see here?
Look like a feedback.
Yeah, some kind of feedback. So feedback from X, in fact. So it's actually positive feedback because as X increases, this rate increases. So the rate increases as X increases. So it's positive feedback. So it looks something more like that.
Oh.
Okay. But the other thing it has a 0.1 at the beginning. So there's always a basal rate. It never gets to 0. Right? It never hits 0, this reaction rate. It's always greater than 0. And then it goes up from 0.1 up. Okay. Okay, so let's so why don't you run this then, see what you get. Oops, I didn't mean to run that. Get rid of that. Let's clear this. Okay, so let's run it. So actually, I might as well put some here. X equals, I'll put a space. There you go. So if you run it, you should get X equals 0.1447 something, right? Do you get that?
Mm-hmm.
Now, do you get that?
Wait, you mean run this in the Jupyter?
Yeah.
Okay. Haven't loaded.
X.
The next thing to try,
Yeah.
try increasing K2 to 1.4. Oh, that didn't work. Let's go higher, 8.4. No, it didn't do it either. What? 18.4. Oh, I'm doing the wrong thing. That's why. Sorry. X, push it to 1.4. Let's see what happens. So let me clear this. I'm going to clear this and do it again, okay? Show you. So first of all, we had it at 0. Gave us that steady state value. And now I'm going to put it up to 1.4. And I get that value. Did you get those two?
Right.
No.
I mean, if you want, you can do it down here, of course. You can go like this. So I can set that, push that back to 0. And then X equals 1.4. And then run it. There you go. You get that? Okay.
Yeah.
Yusuf gets it.
1.2. Yeah.
1.3 and 0.14.
Steady state.
What is going on here?
Wait, that is the concentration of X at steady state?
Yes. And look, it looks like there are two. I can confirm it's steady state because I can say print out the get rates of change. Let me see, is that it?
Yeah.
No. Oh, it's S. There we go. Yeah. So if I print out the rates of change in each case, they're both 0 or close to 0 anyway. So these are two completely different steady states for the same model. You agree with that?
Yeah.
What do you think, Dan?
Yeah. Okay, I'm loading it.
Are you still loading it?
Yeah.
Okay.
All in steady state. Then R does X.
So in order to investigate this, you're going to do some plots, okay? Got it yet, man? Do you want me to send you this script?
Yeah, no. I got the one that you're running on the that you put on the Zoom.
Uh-huh.
Yeah.
It work?
It's still loading.
Still loading? What do you mean still loading? Share your screen. Oh, it's Colab, is it?
No, it's like a Jupyter notebook.
Yeah, in Colab.
You would need to allow me to share with this.
Yeah, you can share. Oh, yeah, sorry, I have to stop. Yeah. Okay.
Okay, I think it's running now.
Share your screen and see what's going on. Need to figure out how to get all 3 screens on at once.
Do you?
We should be able to. That'd be really good, that would be.
It start up a little bit slow and then just.
Okay, there you go.
It's so long.
Is it running then or what?
Yeah. Okay. So this 0.4.
Oh, it took 35 seconds. I'll put 0.7 seconds. Okay, so you've got the 2 steady states then.
All right.
1.3095, and the other is 0.1447. Okay. What I want you to do now is to plot a graph, two graphs on the same, was it two plots on the same graph? Is that the way you say it? One plot should be, so the x-axis will be x, okay? The y-axis will be v1 and v2. Those are the two plots, v1 and v2, as a function of x. So why don't we try that? This might require you to do some thinking. How can we, you stop? This was,
Okay.
yeah, okay, stop, okay. Do you want to start? Okay, you stop your sharing. So let me see if I can, is there any way I can get all, multiple participants can share simultaneously? All right, so
You
in
say the
theory,
one,
you can share now.
yes, I can.
Multiple participants can share simultaneously, it says.
But I couldn't see your screen then.
No, I don't understand that. See if there's a Zoom video I can watch. Yeah. So I want you to plot v1 and v2 as a function of x.
Function of x.
Ones or all plots. Simulate and then V1 so just show V1 Oh, there's nothing.
Yeah, you can't do lots of screens at once. So, okay, we'll do some plotting then, right? So I'm going to do it the really hacky way.
Yeah, but it's not plotting anything.
Oh, you need to import the
Matplotlib, but no, but
yeah, matplotlib thingy.
it's imported, but
Where the hell is it? Oh God. Oh, I put it here, didn't I?
matplotlib.pyplot.
Okay. Yeah.
Just but not show up anything.
Okay. So let's plot. So I'm going to plot v2 first because that's the easy one. So I need to set up x equals to 0. And then I need to compute y1. So y1 is r dot v2, okay? Actually, no, sorry. y1 append. So I'm collecting the y1 values. I also need to collect the x values. There you go. And then I need to increment x. And that's it. Oh, invalid syntax, yeah. No module, matplot, matlib.
Matplotlib. Yeah.
Okay, so I have a bunch of x values, I have a bunch of y1 values. So if I plot these,
It's a pen.
I get that, which is exactly what I expect. I'll do it here.
Oh,
Okay.
they're linear.
Well, that's linear because this is linear. Yeah.
Mhm.
Okay. How do I set the screen size? I can't remember.
You have to do. Yeah, you can make figure, dot figure, and then fix size inside. Yep. Equal. Yeah. It's a tuple.
Oh, there you go. Okay. All right. So next one to do then is y2. So let's have some space for y2. And then I'll put, actually that should be called y, that should be called y2. So let's call that y2 because it corresponds to v2. All right, so I'll put another one here ready for the actual y2. There you go. Y1, y2, that should be y1. R dot v1. There you go.
Oh, okay.
Like 10. 1 second.
Oh, when you're ready, share your screen. Tell me what you get.
So y2. Then
So y1 is like an S-shaped curve,
Yep, it is.
and y2 is a linear one.
Yes.
Yeah.
And at 0, the y1 should start at about 0.1. There you go.
Yeah. Okay.
Okay.
X,
So
y1.
let's put a few more data points in here. There you go. It's better. So this is just V1 and V2. Okay, that's all this is.
Yep.
Now, are you ready now, or are you still doing it?
I have a little weird curve. It's like
Show screen then.
let's see. Oops. This one.
Show screen.
Is it because of trunking?
You're probably going too far. You're going. Your x-axis is too long.
I see. R dot x plus.
Yeah, plus
yeah.
0.1 or something.
Yeah.
Yeah. There you go.
But you say the y1 is linear
No,
because
y2 is linear.
Yeah, we just changed the names, I
You
think.
change them to match. They all matched. Yeah.
Oh, okay.
Yeah. So yeah, the y2 is linear because it's just k 3 times x.
Yep.
Okay, so what can we say from this curve then? So they cross over at 3 places. They cross each other, okay?
Mhm.
Now these crossing points are when v1 equals v2 and the two rates are the same. Because the y-axis is v1 and v2, right? So where they touch, that must be where v1 equals v2. Do you agree?
Right.
Yeah. Of course, when v1 equals v2, that's actually also the steady state. So these, oh, am I sharing my screen here at all? I wasn't. Was I sharing screen? No, I wasn't. Okay,
No.
now I am. So you see the 3 crossing points. So if I, here's the annotation thing. Annotate, okay. draw. Okay, so here's one, here's another, and here's another. Okay, all these are when V1. It's not a very good V1. V equals V2. Ugh, okay. But all these places are when V1 equals V2, and that's the steady state. So this system appears to have 3 steady states. Okay.
Okay.
Yeah, 3 steady states. So let's have a look at, so this step now, the line, if you drop a line from the intersection point, that's actually the steady state level of X. I can't draw the X's. So that's the steady state level of X. And now it's what, 0.1 something?
1.7.
And the computed one is 0.1447. The other crossing point is this one here. Actually, you've got a straight line. Is this one here. That goes all the way down to here. And that's at about 1.3. Okay, so that corresponds to the upper steady state, all right? So I have that one and this one. Okay, so what about this funny one in the middle? Okay, which is about 0.65 or something. We can do an experiment here, right? Let's move the X value up a bit, okay? So if I move the X value up a bit and I extend the line up here, okay? You notice that this is the value for V2 and this is the value for V1.
Mhm.
You'll notice that V2 is bigger than, let me see if I can draw that. V2 is bigger than V1. Do you agree?
Yep.
Okay. So V2 is bigger than V1. Oh, that's not right.
Wait, isn't the curve V1?
Yeah,
Yeah.
V1 is greater than
Yeah,
V2 at that point.
Yeah. I was going to say it wasn't quite working. So V1 is greater than V2. Now, if V1 is bigger, that means there's more X coming in. So if there's more X coming in, then X is increasing. So if X is increasing, X will start to move to the right on the X-axis. In fact, it'll keep on moving until it hits this steady state here and then stops. If I were to decrease it, the opposite happens.
Mm.
You notice now that the other way around, okay? And that means now that X will start to fall, continuously fall, and so it'll continuously move until it hits this steady state. So this steady state here, we say is, actually I can just type text, can't I? We say is unstable. Okay, that one is unstable. Because if you make any movement on either side of it, the system will either evolve to the upper steady state or the lower steady state. You can do a similar kind of thought process for the upper one and the lower one, and you discover those are stable. Okay. So this one, and this one, those two are in fact stable. Those two are unstable. Sorry, those two are stable. This one's unstable. So there's 3 ways to satisfy the steady state here. 3 ways. And they have different properties. 2 of them, one of them is low and stable. The other one is high and stable. And then there's one in the middle, which is unstable. Okay. Does that one make sense?
Mm.
I mean, even if intuitively it's a bit odd, it may not make sense, but at least graphically that has to be the case. So how can I find this middle one? Because obviously I can find this is the low one, this is the high one, all right? So there's actually a poor man's way of finding all the steady states. So if I give you this in the chat, this little bit of this little script,
Yep.
what it does is it randomly sets X and then computes the steady state. Now, whichever one you land on depends on how close you are, depends on how close X is to the starting point, all right? Now, I should say this is unstable. This thing is only unstable in the time domain. So when you try to do a time course simulation, the system will move away from the central point. The steady state solver doesn't use time. It's a gradient descent solver, right? It just looks for the closest minimum. So in fact, we can use the steady state solver to find this unstable one, right? So what I'll do is I'll run this then, okay? Let me clear that. Okay. So I just ran it. I got all these steady states are the same, except this one is slightly different. 0.68. In fact, that corresponds to this piece here. So let's reduce
because the random point it go close to the unstable and
it was close to the unstable one. Remember, the steady state doesn't do a time course simulation. You won't be able to do this if you try to use simulate. It won't work. It'll always move away from this steady state. I'll show you that in a minute. Let's drop this maybe a bit to 6. Oh, there we go. That's better. So now it's found, there's the unstable one. Found a bunch of the upper one. It found one lower one. It found a bunch of upper ones. And it found another 2 unstable ones. So this is sort of a poor man's or poor person's way of finding all the steady states in the system. So if I do it again, I'll get a different set, of course, because I'm randomizing them all. I wonder if you could do a fancy plot here.
So what if you have the X above 1.4?
Oh, it'll always find the upper one, I think. It'll always find the upper one.
Okay.
That's why I put it at 1.4, because I knew it was above 1.3. So it's up here somewhere, you see. It's way up here.
Right.
So it's likely to find the top one. Yeah, I don't know if this, if I drop it more, it'll probably get a more, I don't know whether you can do anything fancy here. Anyway, so that's, so the other thing we can do is we can look at the eigenvalues to confirm. I'll send this to you as well, okay?
Yep.
So these are the 3 steady states that were computed, okay? The low one, the middle one, and the upper one. So at this point, we might not know which is stable and unstable, right? We've just confirmed there are 3 steady states, but we may not know which is stable, which is unstable. But by computing the eigenvalues, we will know. Here they are, they're here. So 2 of them are negative. The middle one is positive. So the middle one is unstable because it's positive. Remember, positive eigenvalues means unstable. Negative eigenvalues means stable. Okay. So last thing I can do is, and I'll give you this. This will plot this one here. We're doing a plot. Well, I'm doing a time course simulation, and I'm setting the X value very close to the unstable point. Okay, so it's starting at roughly 0.68. It takes a while, but eventually diverges to the low one. So it's really close to the it doesn't move very fast off that unstable point, but once it gets far enough away, it really accelerates and quickly drops to the low one. I can probably increase this a little bit to see if I can get it to the top one. There he goes, and I can take it to the top one as well. All right. In fact, what you can do is you can go for I in range. Let's see, you can do 10. What I'll do is I'll take this down to 0.1. Whoops. 0.31. I'll take this out. I'll do the simulation. Actually, I'm going to do my own plot here. M time M, I think that's X, isn't it? Let me just check that works. Or did it? Yeah, it did. It did work. Yeah. Okay. So what I'm going to do is actually I'm going to call this start. Oops. All right. And I'm going to go X equals start. Then what I'm going to do is I'm going to increase start very small amount. Maybe there's something like that, right? And then plot it again. Let's see what happens, shall we? Ah, there we go. Yeah, I think maybe if I dropped it a bit more. Oh, there you go. Yeah, not too bad. Let's get the fig size up a bit. There's fig. Where did you do the figure? Yeah.
So here, like you get the X is really close to the unstable.
Yeah.
But how's the when you randomize it and it's
I'm not randomizing it here.
No, yeah, you're not randomizing here, but like when you randomize the thing on top, and it could find a unstable steady state.
It could, yeah.
So I don't know, like why you couldn't find the unstable steady state in this step.
I set it. I set it very close, right?
Yeah.
But it doesn't. But you notice it doesn't stay there. After about 20, or just before 20, it quickly diverges. I can't stay there. The only way to stay there in time is to be exactly on it.
Wait, so that means the random value exactly go on it?
Well, if I put this one, let's say if I, yeah, let me do this one here. Let me do another plot down here, right? So I'll set that to that very precise one, and then I'll run a simulation here. All right, I'll run, let's see what happens. There you go, see? It's dead straight. In fact, it won't, I don't think it'll diverge, I don't think. Won't diverge. If I'm exactly on it, it'll stay there.
Okay.
But maybe if I make a slight change, that's pretty stable on that unstable point.
So the gradient descent could find the unstable.
Yeah.
Point.
The gradient descent will find it.
Okay.
There's supposed to be an ODE trick, and that if you run the if you run the integrator backwards, so instead of increasing in time, you decrease in time, it will find the unstable point. I've never tried that, but a colleague of mine tells me it'll work. Now, this is pretty, it'll flip in a minute, I'm sure. Wow. Takes a lot to make this. It must be now, it'll change now. And there it goes, it changed. So yeah, anyway, it's yeah, you have to be pretty precise, at least 10 to the minus 7 in order for it to stay put. Where was I before? Oh, 6. Okay, there it is, yeah. Rosa did 5. Because it changes very rapidly. It changes very rapidly once it changes.
Right.
Changes very rapidly. I wonder if I can get it to push out a bit more. I can get it to push out a bit more. Yeah. Anyway, you can have fun all day playing with this. Yeah, it's flipped. Anyway, yeah, it's so these unstable points would not exist in a cell because there's so much noise that it'd be quickly kicked out. So you'd never see a cell sitting on an unstable state, I don't think. Because of the so much noise in the system would kick it out. Okay. All right. That's that for that one. I mean, it's a nice thing having, a system like this that this nice thing about Python, you can do all these kinds of quick hacks, just by writing code, and Roadrunner gives you all the information you need and makes it very easy to mess around with these kinds of things. So
how you get the negative feedback?
Oh, negative feedback is easy. You just take that away. Negative.
Oh, just the bottom part is bigger.
Yeah, yeah. So if you want, what we can do next week is show you what happens when you have 2 positive feedbacks. That's a lot more interesting. All right.
Yep.
Okay, good. And then after that, we'll do what happens if you combine a negative and a positive feedback. Something interesting happens there as well.
So like, for example, like the rate law it's not, sometimes it's not well defined, right? Like we try to estimate it like X.
Yeah, I mean, I just made it up. I mean, I knew that. I mean, we know that some, enzymes behave. They show S-shaped behavior. So I'm just throwing in some S-shaped behavior. I mean, there are different ways to create S shapes, but as you can see, it doesn't really matter how you create the S shape. The key is that you get 3 intersections. Right? It's getting the 3 intersection that's important. So it doesn't really matter how you implement the S shape itself. But just an easy way of doing it. The reason I also lift it off 0 is because if I don't lift it off 0, you get it's not as interesting, because if I take it off 0 and I plot them, and I'll do this, I'll do show so I don't converge on the others, so don't overlay on the others. Oops. Oh, it doesn't even like it. Oh, interesting.
Wait, you have to run from the top. Something.
No, I am running from the top. It didn't like that.
Oh.
It doesn't like that steady state, I guess. Wow. Okay. Doesn't like it at all.
Maybe like 10 to the negative.
Oh,
6.
look! Oh, look at that! Look at that! This is very peculiar. Oh yeah, because the 0.4, of course, basically 0.1 lifts the S shape up and down. So I brought it down. So it's starting off at 0. So one of the steady states is 0, which is very uninteresting, right? This one, I'm not sure if that is actually a steady state or not, because it depends whether that blue line actually is intersecting the orange line or not.
Like a tangent line.
It's almost like it's interesting that if I ask it for the steady state, it fails.
Oh,
And it says it's at infinite, it doesn't get it. Let me see if I set it to X and then ask it to get the steady state. Yes, okay. If I set X to 0, it'll find that 0 steady state. If I set it to something else, like say 0.1, it still finds it. I suspect it. Okay. Let's lift it up a bit more then. Let's go to 0.5. You can't do it. And the point, yeah, it doesn't like it after this. I bet it's okay up to about 0.25 or something before the curvature, before it goes up there or something. Let me see. Rx equals 0.25. Yeah, that's okay. 6.
No,
No, this was okay.
like it's about 0.3 or something.
Yeah. No.
Oh, is it 0.3?
Well, not here.
Oh,
Maybe
so
maybe I've not passed the curve yet.
Not powered. It's 0.4 or something.
It's 3.5. It's 3.5. No.
Look like 0.4 or something.
But
Oh.
it's starting to. It found it, but there was a little bit of effort for it to find it. Now it fails completely.
Yeah, 4 and 5.
Yeah, it fails. Yeah. So something happens here. You pass the second derivative when the second derivative is 0.
the inflection point.
The inflection point. That's right. That's the name for it. After. So I don't think there is a steady state above 0.4. There isn't one. So this is only one steady state, and it's actually unstable. In fact, let's do a simulation of this, shall we? So let's go 0.1, and then no, it's dropping to 0. Okay. Oh, that's dropping to 0. So actually, that must be stable then, is it? Oh, it is stable.
I mean, it's the Rx is now set as 0.1, which means
Well,
that it's stable to 0, right?
Let me just make sure it's at 0. Okay.
It's negative.
It's stable. So that
Wait.
0 point is actually stable. That's stable.
Yeah.
Wait, I thought the positive is stable.
No,
But-
negative is stable. Positive is unstable.
Okay.
So okay. Now if I set x to 0.5, all right, and then do a time course simulation. I bet this is unstable. I bet there's no steady state, I suspect. No, there is. Okay. Go a bit more then. It's starting to find some difficulty. Maybe I have to go beyond. Oh, for the time course, maybe I have to go beyond this point. Maybe beyond the 1. Let's go up to 1.
Or 1.2.
Let's go to 1.3, 1.4 to make sure. It's interesting. Okay. 5.
Ooh.
Weird.
Yeah, so still can find stable.
Yeah, it still goes to the stable one. I guess there's only one steady state then. Yeah, there's only one steady state, and it's stable. Now, of course, the minute I lift, this minute I lift it up a little bit. Hold on, yeah, the minute I lift it up a bit, if I rerun this, let's go to 0.02. you can see there's two intersections. So
Mm.
in fact, this is called a bifurcate. This is actually a bifurcation parameter. As you change it, the number of steady states changes. So when it's low, you only have one, and then when you have more, when it's above 0, I presume, you get another 2 forming. Now, if I push it up enough, no steady states. Oh no, there will be one way up here somewhere, way up to the right. Let me bring it down a bit.
Mm.
So there's 3 again, right? And if I push it up to 0.3, there's only 1, which is way up here. If I do that 100, you'll see it. There it is. See, it's just 1. Not stable.
Mhm.
All right. So you could imagine, this could be something that a cell could manipulate, and by doing so, it could manipulate the number of steady states. So it could move the system into a bistable or non-bistable regime if it wanted to. All right, I think that's it.
All right.
Okay, so next time we'll try something different. We'll try adding 2 positive feedbacks.
Yeah, I was asking about the perturbation. Like, one stoichiometry, you can get the multiple perturbation matrix or no?
The perturbation matrix will just be gets scaled, depends on the concentrations of the fluxes, but there's only 2 here. It's a small matrix. That's the perturbation matrix. So if I perturb V1, I get that percentage increase in X. If I perturb V2, I get that percentage decrease in X.
Is it always the same?
In this case, it will be. If there's 2 steps, it'll always be the same. Yeah, they'll be opposite each other. There's a theorem called the summation theorem, which states that the sum of all the perturbations with respect to a given species will be 0. So we haven't done that. We could do that the week after next.
Yeah, that's what you think.
Okay. All right then.
Right.
Thank you.
No problem. See you next time.
Bye.
Bye-bye.